So in this episode we're looking at negative acceleration and how you can accelerate yet still be at a constant speed. So just before we begin, I want to recommend a prerequisite of the acceleration video that I did. If you ever want to see it, just search for acceleration and fun physics assistant on YouTube and it should come up. And if you don't watch that video, I would recommend that you have some background knowledge in the acceleration formula. If you don't have either of these, then I will only be skimming over a brief bit of the acceleration formula, so you may need to pick it up either quickly or just go back and see one of these videos first. It doesn't take too long. The acceleration video explains everything you need to know, but I will go over it quite briefly here. So when we're looking at negative acceleration, we're looking at the velocity final being less than the velocity initial. So again, acceleration is velocity final take velocity initial over time. I won't go over that, but if you do want to see how that works out, then I recommend seeing the initial video. So if we have an initial velocity where we are basically, say, at 60 kilometers of speed, and our final velocity is, say, 30 kilometers, then that would suit that condition there if that was the initial velocity and that was the final velocity. For this, let's have a look at an example of, say, someone running where initial velocity is, say, 30 meters per second, so obviously they're a good sprinter, and the final velocity is 10 meters per second after a certain distance. So let's say it also took them 4 seconds to slow down, which is pretty reasonable for a sprinter, but let's have a look at how that would work in terms of velocity and acceleration formula. Essentially what we'd get, because it's initial velocity take final velocity take initial velocity, we would get 10 take 30, all over a time period of 4 seconds. So we would get negative 20 over 4, and we'd get negative 5 meters per second squared. Now, essentially what's happened there, if I just focus in, is we have had a faster initial velocity here, and we've had a slower final velocity. So therefore, we have a negative velocity because they're slowing down. They're not getting faster, so therefore, for every meter per second traveled in velocity, they are decreasing 5 meters per second per every second. So that's essentially what's happening there, and that's how we get negative acceleration, by having deceleration or something slowing down. Because, of course, the change is a negative change, it is slowing down, it is not increasing per second. I hope that makes a bit of sense. Again, the prerequisite is needed for the acceleration video to probably fully understand this, but it's just showing you basically, mathematically, when something is slowing down, you essentially get a value that is a negative value because there is a negative increase, or a decrease, if we want to put it that way, in the distance covered every second, so therefore the velocity per second. Now, on to accelerating at a constant speed, and this is another example that fits in with the first episode, but I'll explain it again for those who haven't seen it, and that's about a car travelling around a curve. So let's say we have the car here, and it's just gone around the curve. So while it's on the curve, believe it or not, it's actually accelerating even if the speedo registers 50 kilometers per hour for the entire distance of that curve. In fact, the P shouldn't be in there, sorry. And how does this work, you ask? Well, remember back to what I said originally when I was talking about displacement and velocity. We have a scalar, and that's things like distance and speed. And then we have a vector quantity, which is, as I said, velocity and displacement. They're probably the two best examples. from this, we can actually see why we could consider that car to be accelerating around the bend. And that's because with the acceleration formula, we use a vector, because acceleration is a vector, as is velocity. Oops, sorry. And essentially from that, we are able to see that because there is a presence of the velocity within the acceleration formula, we need to rely on distance because vector quantities, direction, because vector quantities rely on direction and magnitude. So because of this, because the car's changing direction on that curve, the velocity is changing. And because that's Vf over Vi, or a change in velocity, then the car must be accelerating because there's a change occurring, because the direction is changing. And when the direction changes, the velocity changes, so therefore the acceleration changes. And that is why, when you go around a bend in a car, you are technically accelerating because you're changing direction, therefore you're changing velocity, which is a vector quantity where direction matters, and you're changing acceleration because acceleration is calculated using velocity, and therefore direction does matter as well because it is a vector quantity. I hope I've sort of made this clear. It may take a little while to get your head around, but I would recommend even watching the vector and scalar video that I did originally, just to be able to get the idea of the importance of a vector requiring both direction and magnitude. Again, magnitude is just size, so it doesn't really necessarily need to come into this example. But the key word here is direction, because as I said in the original video, if we had a planet with an orbit around it, and we had a satellite there, and it started and finished in the same spot, then it would essentially have a zero velocity because it hasn't moved anywhere, because direction matters. And it hasn't gone in any direction from the original point. However, when it comes to distance travelled, or average speed, or distance or speed there, then yes, there is an actual number there which is greater than 0, because direction doesn't matter, it's just about the journey overall, and the magnitude of that. I hope this makes a bit of sense, but it is something that may take a little while to get your head around, but when you do get it, it should be fine. So that's just a brief overview of negative velocity, and where velocity can basically increase even though speed is constant.